Hello, so in today's video, we're going to differentiate this function here. So the modulus of tan x with respect to x. As you can probably guess, this is going to be a case of using the chain rule to differentiate this, just because we're taking the modulus function of the tangent function. But before we do that, let's just think about the domain of x values in which this derivative exists for. So if you think about like a tangent graph or a sketch of a tangent graph, it looks something like this. So we've got asymptotes at these odd multiples of pi over 2. So something like this. Obviously, yeah, that's pi over 2 there, 3 pi over 2, and so on. And obviously, negative pi over 2, negative 3 pi over 2, and so on and so on. So we know, therefore, that if we sketch the modulus of tan x, it's going to look something like this, roughly. Something like this, with these like pointy bits at these multiples of pi. And yeah, so our red graph, our red sketch is going to be this this modulus, this y equals modulus of tan x graph. And as we can see, yeah, we get these pointy bits at minus pi, 0, pi, 2 pi, and so on and so on. So these are multiples of pi. So we know that you can't differentiate the absolute value of x with respect to x when x equals 0. This is undefined, so this is undefined. So therefore, we can't differentiate the modulus of tan x at these multiples of pi, and of course we can't differentiate them also at these odd multiples of pi over 2. So therefore, we actually can't differentiate this function at any multiple of pi over 2. So therefore, the domain is going to be essentially all real values of x. So the domain, or the values in which values of x which give us a defined derivative, will be this. So derivative exists if x is a real number, but not a multiple of pi over 2. So apart from the multiples of pi over 2, where k is just some integer. Okay, great. So we now know where this function has a derivative, an existing defined derivative. Let's go and differentiate it. So as I just said, this is going to be a case of using the chain rule. So applying our chain rule formula, we get the derivative of the modulus of tan x, but differentiating that with respect to tan x, and then multiplying that by the derivative of tan x, but with respect to the variable x. Okay, and again, this is just an application of the chain rule. So yeah, we know that when we differentiate, I mean, let's just make a note of this down here. We did this in a previous video where we differentiated the modulus of x, and we got this result here, modulus of x over x. So we know that when we differentiate the modulus of tan x with respect to tan, we should just get the modulus of tan x, but over tan x. Okay, so we get that. And then when we differentiate this tan function with respect to x, again, we did this in a previous video. So differentiating tan actually gives us sec squared. So sec squared of x. So yeah, we've got these results here, and we can just apply those results to our formula up here. So we get sec squared of x there. And yeah, so that's our result then. So when we differentiate the modulus of tan x, we get modulus of tan x over tan x multiplied by sec squared. I guess we could simplify this a little bit. So we know that this is the modulus of tan x over tan. And we also know that sec squared is just 1 over cos squared by definition. I guess if we just go to a new page to continue this. So modulus of tan x over tan x multiplied by 1 over cos squared of x. Now we know that tan is just the same as sine over cos. So this is actually just the same as the modulus of tan x over sine x over cos x multiplied by cos squared of x. So now what we can say, well, we know that one of these coses will cancel out, so that will cancel out with that there. So we just get the modulus of tan x over sine x times cos x. Okay, we get that. Now we know from trig identities that sine of 2x is equal to 2 lots of sine of x times cos x from the double angle identity. So what we can say therefore is that this this value on the bottom is just going to be a half of sine 2x. So this is the modulus of tan x over half of sine 2x. So in other words, this is just 2 lots of the modulus of tan x divided by sine 2x. But of course we know as well that well, 1 over sine is just the same as cosec by definition, so cosec of x. So actually what we get, if we just sorry, let me just make this writing a little bit smaller. So what we get in conclusion is we get 2 lots of cosec of 2x multiplied by tan, the modulus of tan x. So this result here. So yeah, that is actually our final result here. So 2 lots of cosec 2x times by the modulus of tan x. Yeah, so when we differentiate, just to summarize, so when we differentiate the modulus of tan x, we get 2 lots of cosec 2x multiplied by the modulus of tan x, and the set of values in which this this derivative is defined for will be all x numbers in the real numbers, but apart from these multiples of pi over 2. So apart from any multiple of pi over 2, this will exist. So for all x in the real numbers, well, apart from these multiples, so pi over 2 multiplied by k, where k is just some integer value. So yeah, that is our result for today's video.